Hello, my name is Ojok Esther, and I'm a IT student at Makerere University. And our project is a graph-based reasoning tool for preeclampsia self-screening using accessible biomarkers. Uh, Preeclampsia is one of the leading causes of maternal mortality in Uganda, and the challenge is because early detection is extremely limited. Women in rural and semi-rural communities often lack the regular antenatal monitoring due to distance, costs, lack of equipment, and also shortage of skilled health workers. And most of these cases are identified late when the symptoms are already progressed to those very high dangerous levels. And this creates preventable mortality and complications and emergency C-sections and a lot of these long-term cardiovascular effects. And the traditional clinical tools rely mostly on hospital-based monitoring, blood pressure machines, urine dipsticks, and the lab biomarkers. But this AI allows us to detect the risk early, even before the symptoms have started to show, and also and it does this by identifying the patterns in the simple inputs. We use graph-based models like GAT and RGCN, which are extremely powerful here because the maternal health risk factors are interconnected, like age influences blood pressure interacts with the proteinuria, and these symptoms also relate with severity. And this AI helps us to uncover those subtle relationships that might be very difficult for the physicians to observe manually. So instead of relying on the physical clinical visits, here we provide a low-cost digital screening tool that's accessible everywhere. The keywords in our project are preeclampsia screening, which is the early detection and risk assessment of preeclampsia, the accessible biomarkers, these are the measurable indicators like the blood pressure, mobile health is the use of mobile devices to support healthcare services and data collection. And then maternal healthcare diagnostics, this is the assessment and detection of health conditions affecting pregnant women with the aim of improving maternal health. Then resource-constrained AI, these are systems that are able to run locally on devices and operate under limited processing power, memory, connectivity, and energy availability. So these are some of the works we looked at that are related to ours, the literature review. And our search was mostly based on the clinical background of preeclampsia, how blood pressure and the symptoms relate to the disease progression. We had machine learning in maternal health, then the graph neural networks in healthcare, and the deployment approaches focusing on the lightweight APIs and all that. And we identified some gaps, which were the architecture and practical limitations. And yeah, our problem statements are the domain application problem is, I've been talking about this all this while, how preeclampsia is the leading cause of maternal deaths. And this is stemming from late screening. And then our computational problem is that our inputs are comprised of demographic data like age, gravidity, parity, and then the vital signs, and also the lab data. And using these features, our model learns from them, learns each unique pattern, and does binary classification of either high risk or low risk. So among the gaps we identified in our literature review, we came up with our objectives, which were to develop a supervised machine learning framework for prediction of high or low level preeclampsia based on the clinical features, to implement and compare graph neural networks, to identify the influential features for clinical explainability, and to evaluate the model performance. Also, to develop an edge AI that is accessible for preeclampsia prediction. Our research questions were: how efficiently can a supervised machine learning framework predict higher low risks of preeclampsia, and how GAT and RGCN models compare in terms of predictive accuracy and robustness for risk classification, and which nodes and clinical features are most significant, and how the edge AI system can be designed and deployed to provide real-time accessibility. These were our research contributions and the outputs, and this is our system architecture. Basically, how our system works: when we get the data, there's the graph formulation layer, there's parallel processing between the GAT and the RGCN, and then we have the ensemble layer, because the model we chose at finally was the ensemble of GAT and RGCN. Then we have our feedback and then the learning loop. Then this is our model architecture for RGCN. So here basically how RGCN works is, yeah, we input our features, and then remember, every patient is a node in RGCN. So RGCN basically learns the relationships between every patient and learns from them, and then it gives you that output of either low risk or high risk. Yeah, each patient is a node, and every node carries a clinical feature. And then, sorry, each node carries the clinical features. And then the edges are created between the similar patients using the KNN, and this results into a patient similarity graph that captures the relationship of the clinical data. So yeah, those are the mathematical foundations of RGCN. And then this is our model architecture for GAT, and it works a little bit like RGCN, just that here in GAT, the way GAT works is still every patient is a node, but here instead of relationships, it assigns attention weights to each feature. In our case here, every maternal feature like systolic blood pressure, diastolic blood pressure, and the symptoms is treated as a node in a graph. So what GAT does, it performs 3 key operations like feature embedding, where every feature is transformed into a land vector representation. And then it also does attention scoring, where every pair of the connected features, the model computes how important one feature is to the other. For example, systolic BP may receive higher attention when proteinuria is high, and then age might get low attention when the symptoms dominate. So yeah, and then it also does weighted aggregation. Here, weighted aggregation, the model aggregates information across all features, and it weighs them basically weighted by their importance, which means that GAT learns feature interactions dynamically based on each patient's input, not just static rules to follow. Yeah, and this is the mathematical foundation. Then this is the model, our model's architecture for the GAT and RGCN ensemble. This is where I put the data. This is the parallel processing, GAT and RGCN, and then that's a prediction layer. That is the ensemble's mathematical foundation. And then our data set. Our data set includes key maternal features like systolic BP, diastolic BP, fluid proteins, age, and all that. So we cleaned and encoded the data. We did the data pre-processing, and then because our data set was relatively small, we did some feature engineering to allow our GNNs to perform more effectively. Yeah, that's how we did it. And then this is a feature importance. That was our graph construction. Then this is comparing our models' performances, where you clearly see that our ensemble performed much better than the other models that we used. So, and it was then that we actually selected. So we selected it because it combines graph level feature representation with attention-based contextual weight. It also handles the small data sets relatively more efficiently than the others. It also performs the single models in RIPPLE and aligns with biomedical graph literature, where relational patterns are vital. And then we deployed our model on, we did our web application, and we deployed the back end on Brenda. And then the front end, we deployed it on Netlify. Yeah. So basically, after the model was trained, we got the ensemble file, and then we have a Flask API that loads the model logic. And yeah, we have a REST endpoint that accepts the JSON input and from the front end, and then returns risk prediction. And then this is our system architecture where the user enters data to the web user interface, and then to the Flask API render, to the ensemble file, then there's ensemble inference, then you get the risk output to the client. So basically our deployed model allows real-time preeclampsia risk assessment, prediction, based on the key antenatal parameters. And then because the users send the data and then get a response of the risk and the confidence level. So our application is accessible via this link. You can check it out. And then our limitations were our dataset was small, and we also had unavailability of some of the features that we wanted, like the dipsticks and the edema images. We also lacked a data dictionary for the dataset that we got. So we made our own data dictionary, which is this. And then in future we hope to add the computer vision aspect to our project to make better diagnostics and improve its accuracy. And yeah, and since yeah, that's what we hope to do. Thank you for listening. Those are our references. Thank you for listening.